here's this is not really it's a toy motivation for this problem. It's just a story. If you string up a string of light bulbs, in series, you plug in a battery, all the lights glow at the same rate. But if you have an electric blanket, right, so it's a network of resistors or heaters, heating elements, and you plug in a battery at two different points, I don't know if that picture came out. Yeah, the heaters will not the energy will not be the same on each heater, so that your partner, whoever sleeps on the left side of the bed, is going to be cold. So the goal is to, can we design given a graph, can we design a set of conductances so that all the light bulbs or all the heaters have the same amount of energy flow? They'll be glowing at the same rate, or maybe you think of it as a computer screen or something. I don't know. So that's the problem. Can we adjust the conductances on the edges for the light bulbs so that the bulbs glow with the same brightness? Okay. Very simple problem. So let me turn it into a very simple mathematical problem, classical mathematical problem. First of all, the Dirichlet problem is when you fix the conductances. So we have a graph, G. Right, here's our graph. I'm going to label the vertices here. And on each edge, I'm going to have a positive real conductance, C. All right. And I'm going to have a certain subset of the boundaries, a subset of the vertices called boundary vertices. And for essentially, for most of the talk, it's just going to consist of two vertices, the one on the top and the one on the bottom, where I hook up my battery. And so, you can think of the boundary values of the Dirichlet problem as being 1 at the top and 0 at the bottom, and then I will have some flow of current through the network. And the Dirichlet problem is to find the equilibrium potential. That is, in mathematical terms, it's the harmonic function on the vertices, on the internal vertices, f. So I'm looking for a harmonic function. So it's a real value function whose boundary values are equal to the given boundary function u, but it's otherwise harmonic in its side on the internal vertices. And what harmonic means in this context is that you take f, at a point, and you sum over all neighbors of the difference between f of x and f of y, weighted with the conductance function c. So if you like, the value at every point is a weighted average of the neighbors, if it's harmonic. Okay? Hopefully that's familiar to most people. Any questions? Okay. Well, of course, one way it's just a linear algebra problem to find this harmonic function. Alternatively, you can minimize the energy, so-called Dirichlet energy, which is the sum over all the edges, the difference of the function squared times the conductance. So we're going to call this quantity the edge energy. That's the amount of energy dissipated by that light bulb along that edge. Okay, so now when we have a harmonic function, it induces, there's a current flow associated, and that gives you an orientation of the edges, at least as long as the current is non-zero on every edge, you will get an orientation of the edges. So think of the edges as going in the direction of the current. At the top, where you plug in the positive terminal of the battery, it's going to be a source of current. And at the bottom, you're going to have a sink of current, but there are no other sources and sinks. So what we get is an acyclic orientation of the graph, which has no sources and sinks except on the boundary. Right? So these are called, in the case when there's only two boundary vertices, these are called bipolar orientations. They're acyclic orientations with no sources or sinks except a single source and a single sink. Right? But more generally, the orientations which arise in this context can be defined, it just means that they are the Yeah. Well, well, you just look at all functions which take the correct boundary values and have no interior extrema, and then you look at the associated orientation defined by that function. You look at df, which is a function on the edge, and look at its sign, and that defines the orientation sigma. So one thing to define this space of all orientations is just a finite set for a finite graph, and that's the set which we're going to be interested in. Okay, now I'm going to call capital Psi this map from the conductances, the choice of conductances, one for each edge, to the set of energies. And the conductances are going to be positive real numbers. The energies can be positive or zero. If you choose if you're unlucky, you may get some zero current along some edges by some symmetry or other consideration. So let me just look at, here's an example just to see what kind of map we're dealing with here. This is a very simple network, with 5 edges. Again, the same boundary vertices V1 and V0. And given the 5 conductances A through E, it's a rational map. The energies are just some rational functions of those 5 values. Somewhat complicated looking things. And the goal is to invert this rational function, right? If you give me some desired energies, can you solve this equation for A through E? And well, so here's sort of, in this case, there's two. Well, let's see. In this case, it's a bit of a pain to solve these equations directly, but you can find 2 solutions. And well, let's see. This is if you look at for example, A as a function of the 5 energies. I call the energies E1 through E5. And A satisfies this, well, it's a polynomial in square root of A, a quadratic polynomial in square root of A, which has 2 real roots for any choice of the energies. But it's a somewhat interesting combinatorial expression to try to understand what these coefficients are. Well, we'll talk more about that later. So what's the theorem? The first theorem is that if you take your favorite orientation of the graph, acyclic orientation, and for whatever energy you care to find, there is a unique choice of conductances which will realize those energies and that orientation. That is, there's a unique choice of conductances for which the associated harmonic function, that is the current flow, will realize that data, the data of both the energies and the orientation. So for example, if I want all the energies to be constant, equal to 1, then the number of solutions are going to be exactly the number of acyclic orientations in sigma. Right? If you, since the map is just a rational map, homogeneous rational map, you can actually think of this map psi here, extend it to complex values, and one can show, and that's another result, that the topological degree of this map is actually equal to the size of the set of orientations, which is equivalent to saying that on a given theorem 1, it means that for positive real energies, there are actually no other solutions except the real ones, the ones that are really physically realizable. Okay, and finally, for the number theorists in the audience, there's a algebraic or number theoretic consequence, which is that if the energies I'm looking for are rational and the boundary values are rational, then I'm inverting a rational map, so my solutions are all algebraic numbers, since all solutions are algebraic and real, I actually have the Galois group acts, the Galois group of all algebraic numbers, but in particular just the totally real ones, that's all I need, acts on the set of solutions, permuting those solutions in an interesting way. Okay, so here was the example we discussed. In order to draw a picture, so let me explain how, if the network happens to be a planar network, that's the kind of graph we're used to, we can actually make a picture of the harmonic function in the following way. So here's our network. This is called a Smith diagram. So you associate to a harmonic function on such a network a tiling of a region, of a rectangle in this case, with rectangles. And so to each, let's see, I guess it's easier to go backwards. If I look, let's see, for each vertex in the network, there's a horizontal segment in the tiling, and for each edge in the network, there's a tile, there's a rectangle. So for example, this edge 11 that corresponds to that tile, and the top and bottom edges of that rectangle, join the corresponding vertices over here. I mean, the fact that this vertex is joined goes between black and yellow it corresponds to the upper and lower boundaries of that tile over there. And well, in this picture, the y-coordinate of the rectangle on the right is the harmonic function. It's the voltage, the interior voltage is the voltage on the corresponding vertex over here. And so the voltage that is the harmonic function corresponds to the y-coordinate. The width of each rectangle corresponds to the amount of current flowing along that edge. The current is the width, and the conductance is then the voltage drop. I mean, the current divided by the voltage is the conductance. The current is the width. The voltage drop is the difference in is the height, and so the ratio of that is the aspect ratio of the rectangle. So that's the conductance. And the energy, the Dirichlet energy, is just the area of the corresponding tile. So there's a very nice sort of one-to-one correspondence between the tilings of a rectangle with rectangles and networks with planar networks with two boundary vertices there. So what I did was I found a solution. I started with the network, and I found a solution where all the areas were one. So it's an area one rectangulation of a big rectangle. But in principle, I could find an analogous picture over here with the same combinatorics but arbitrary areas. And you can read off the orientation for this picture by saying which for each edge which of the two what are the colors of the top and the bottom that determines. I mean, since yellow is above green in this edge number 10, that means the orientation is going that way. Is that okay? This is just my sort of running example graph. That was one of the solutions to the equation, that big rational system of equation where I wanted all the energies to be one. And it turns out that there are 12 different solutions to this. The number of orientations is 12. And all of the geometric quantities in this tiling are all the physical quantities are algebraic numbers. For example, the width of that tile number 1 on the upper right tile is the root of some integer polynomial. Here it is. Kind of surprisingly large coefficients, but all integer coefficients. And this polynomial has 12 different real roots. It's totally real. So what do the other 11 roots mean? Well, they are the widths of the other, the widths of tile number 1 in the 12 other tilings, 12 other solutions to the same problem. So this, just to repeat, if I'm looking for energies area is 1 for each rectangle. There are 12 solutions, and there they are. And they're all related by the action of the Galois group. You know, if I take one of these and I apply some automorphism of the underlying number field, it will map all the geometric quantities here to some other tile over there. Right? And so each of these also corresponds to a different orientation of the graph. So this orientation, this particular acyclic orientation, I think corresponds to that tile, that tiling there. And if I apply a Galois automorphism, it's going to move this tile to some other place, and therefore it's going to change the orientation in some interesting, non-trivial way. I didn't know there were 12 solutions ahead of time. I just plugged in my graph, asked it to solve that equation, and it spat out this 12 solutions. So counting the number of bipolar orientations of a graph is an NP-hard problem, but the computer can do it for small examples. Well, so yeah, here's what is this number of orientations? Well, it's a sort of a classical graph invariant. When your boundary just consists of two vertices, and well, let's suppose they happen to be connected by an edge. It's just a minor modification of the graph. Then this number, the number orientation has a name. It's called the chromatic invariant of the graph. It's the derivative at one of the chromatic polynomial of the graph. Or if you like the Tut polynomial, it's the derivative at 0 of the x derivative at 0 of the Tut polynomial. So there we can see Tut appearing again. But in particular, it's an NP-hard to compute this quantity for a general graph. And even, as I understand, it's NP-hard to approximate this quantity. But what we have we have realized this invariant, this NP-hard problem, as the degree of a certain rational map. Not that really makes it easier, but at least it's a different way to approach the different sort of way to approach the enumeration problem. So anyway, let me just briefly tell you how to prove those theorems. I mean, nothing is really difficult here. Well, this is the existence theorem. Why does there exist, for a given set of energies, a set of conductances? All right, we're trying to find a harmonic function, right? So the Laplacian is 0, and this is the harmonic function. Of course, we don't know. We're looking for the conductances. Those are our unknown things. But if we can rewrite this current, right, as the energy divided by the potential drop. Okay. And this equation, 0 equals this equation, the energies are what we're given, and now we can just have one unknown, which is this function h, our harmonic function. And so we can think of this equation, this set of equations, one for each vertex, as it's just a rational equation, or nonlinear equation for our unknown function h. Right, so rather than solving for the conductances directly, let's first solve for the harmonic function h associated to these energies, and it has to satisfy that equation. 0 equals the sum over, this is this, for each x, there's a sum over the neighbors y of x of the energy along the edge xy divided by hx minus hy. So I call this the n-harmonic equation because it's like the harmonic equation, but well, for one thing, it's nonlinear, but I'm fixing the energies rather than the conductances. And well, you can see that the solutions to this equation are critical points of a certain functional, capital M. Well, the functional is just the product over all the edges in the graph of h of x minus hy raised to the power of the energy E, the desired energy EE. Right? If I take the logarithmic differential of this functional, then I'm going to, with respect to h of x, then I'm going to get this expression for each x. And okay, so why does this functional have critical points? Well, let me see. Maybe I should draw a picture. If you instead of looking at, here we're trying to solve for our unknown function h, and let's just first look at the set of h's, the set of functions on the vertices, such that the orientation they induce on the edges is equal to our favorite orientation sigma, right? That's just some polytope, convex set in R to the v, v minus 2, because each of these conditions is just a linear condition on h. And on that polytope, the log of m, if you restrict to that polytope, the log of m is a strictly concave function because it's the sum of logs which are concave functions. And on the boundary of that polytope, there's some edge where h of x equals h of y, and therefore the log of 0 goes to minus infinity. So it's a concave function which goes to sort of your space of all functions is divided into these polytopes, and on each polytope, this function m has a unique critical, it's concave and goes to minus infinity on the boundary, therefore it has a unique maximum. So there's one maximum on each cell of this decomposition of the space of all functions, and each cell corresponds to a different orientation. So maybe I should have put an extra line in there, but so the proof really just fits on one slide. The other theorem is also has a very short proof. Why are all the solutions real? So here's our equation. I give you some positive real energies. Why are all the solutions H real? Well, there's the Gauss-Lucas theorem is some classical theorem about polynomials. If I look at the roots of a polynomial p with complex coefficients, and then the roots of the derivative are contained in the convex hull of the roots of p. That's a Gauss-Lucas theorem. And so when I solve this equation, let's think of there's one of these equations. It's a system of equations, one for each x. So let's just look at one of the equations and think of h of x as our variable, and the h of y's are going to be fixed, right? Then you can see that h of x, if I fix all the values of h, our harmonic function, and all the other vertices, then h of x is going to be a root of p prime, where p is this polynomial here. Right? If I differentiate this polynomial p, I'll take the logarithmic derivative, and I will get exactly that expression. This is not quite a polynomial, but it's essentially a polynomial. And therefore, because it's by the Gauss-Lucas theorem, h of x has to be inside the convex hull of the roots of p, which are the neighboring values, h and y. So if I have a solution to this equation, then at every vertex of the graph, the value has to be inside the convex hull of the neighboring values. But all the boundary values are real, and therefore all the interior values have to be real also because they are inside the convex hull of the boundary values. So I don't know if you appreciate this kind of result, but this is a took us a while to find that. Yeah.
Just a nice question on your. So when you solve the equation for the gravity argument, you have somehow to fix normalization for h or something.
Oh yeah, right. Because there's an absolute value here. But once you fix the sign on each edge, that allows you to remove the absolute value signs. Although you may have to exchange these two guys. But when you take the logarithmic derivative, it always leads to the same equation. Was that your question?
No, but then you can multiply h by any constant and in the solution.
It's projective.
Yeah. So
in which?
No, the boundary values are fixed. The boundary values will occur in that, among those values. Okay. Please.
Little confused.
Okay.
So when we just have a electrical network, we just put the source and sink, then the solution is definitely unique.
Yes.
And it's also
If you fix the conductances, the solution is unique.
yes. And
If you fix the energies, the solution may not be unique.
yes, but if we fix the energy, for instance, but we still have directions, right?
Yes. Then the solution is unique. That's the content of the theory.
Yes, but does it mean that, at least it should mean that if you have the energy and you have an arrow, then energy at the beginning of arrow is lesser than energy at the end.
No, the energy lives on the arrows, on the edges. Right? The energy is the amount of energy dissipated on an edge.
Okay, so,
Right, so it requires it. Yeah.
Okay.
Right, the energy is a function on the edges, and it tells you how much the light bulb glows. Any other questions? Here? Okay, so well, here's a very simple example, which is kind of connects to something else. If I have the complete graph Kn, which well, Kn plus 2. So I have two favorite vertices, which are the boundary vertices, and then I have a complete graph Kn in between, connected to those and connected to each other. And I guess there should be one more edge from the top to the bottom, but it doesn't play any role because the boundary values are going to be fixed. So that functional, which appears in the proof, says that in order to find suppose I want to find a solution where all the energies are 2, then I need to maximize this product of xi minus xj squared, where the xi's are the values on the interior, on the middle, well, all the values really, but I'm fixing 2 of the values, x1 to be 0 and xn to be 1. So that should be an n plus 2. All right. Well, okay, so that's a classical problem. You know, how do you if you put a bunch of electrons on a line segment where you pin an electron at the origin and another electron at 1, and they repel with this Coulomb, two-dimensional Coulomb force, you know, what arrangement do they, what's their equilibrium position? You know, that's what it looks like. Well, the roots of some classical orthogonal polynomial, if you prefer. But there are many solutions, of course, because I can permute the variables. I can relabel. So that's a case where the number of solutions is n factorial, and the degree of the polynomial is n. So you have, in some sense, the maximal Galois group action. Oh, okay, so now we can get to some geometry. There's a very large number. I mean, what I did was I took a 40 by 40 grid, square grid, and I oriented. Well, okay, I turned it on its. I turned it by 45 degrees, so that 1 is at the top, 0 is at the bottom. I mean, that's the two vertices, the boundary vertices, and I orient all the edges, you know, in a descending manner. So I'm choosing this particular orientation, and then I ask, what is the corresponding harmonic function which realizes those energies? And there it is. I don't actually know how many solutions there are. This is a, you know, nobody knows how to count the bipolar orientations of the square grid. It's one of those unsolved problems in graph theory. I'll talk about more of that in a second. But yeah, it looks like it's it's converging to some sort of continuous mapping. No. So what you can do in this, here's another copy of the same picture. I think I took a slightly larger one here, maybe 60 by 60. But now I have all this freedom to change the areas, right? There's a solution for any set of areas. And so, this is something you cannot do with conformal maps, which is, if I'm interested in some detail of this picture, I can zoom in by just increasing the areas of those rectangles there, and the others will sort of get squished away, right? So I chose a deformation of the areas, which sort of allowed me to zoom into some point. And I can, resolve the equations. It's very easy to do that just using that maximum principle. Okay. Well, here's another. This one, I'm sorry, I didn't. I need the slider, which since I converted my slides to PDF, I can't do the sliding. But there is a scaling limit to these equations in this particular context. You take a square grid with that particular orientation, the sort of the southwest orientation, and if I let n get large, then the solution tends to a continuous, in fact, analytic map, which satisfies some kind of interesting looking nonlinear PDE, some analog of Cauchy-Riemann equations, which, well, here it is. If the usual Cauchy-Riemann equations with constant conductance, looks like this. That's what you learn in your complex analysis class. And there's an associated Laplacian operator. Well, if instead you fix the energy and you fix that particular orientation, then you will. Then the analogous equations look like this. Your u and v are the x and y coordinates of the image. X and y are the x and y coordinates of the domain, just like in this case. But there's an associated, I don't know what to call it, nonlinear Laplacian over here, which both the real and imaginary part will satisfy the same nonlinear harmonic operator equation there. But, I don't know how to solve that equation or those equations in general. I can just write down a few specific solutions. You can solve them by relaxation, which is what I did in those pictures. If anybody has some suggestion about what to do now, I would be happy to hear it.
Can you prove that the conductances are bounded in the middle?
They're not bounded. Oh, in the middle. Yeah. I don't think so. Yes, I can. Yes, I mean that follows from the. I mean, you can prove that the solutions to this equation are analytic functions, so they're going to be, in any compact region, they're going to be, continuous and very friendly.
The solutions are analytic, but do not satisfy Cauchy-Riemann.
Oh, they're real analytic. They're real. Both u and v are real analytic functions of x and y. They're not complex analytic. Right. This implies complex analysis. This implies something else. I don't have a name for it, but they're just real analytic. Plus, they satisfy that nonlinear Cauchy-Riemann equation. Okay, so of course, this 40 by 40 grid has many acyclic orientations with one source and one sink. So you can ask, if I do the same, if I just pick a random orientation, do I get some similar kind of geometry? And I don't actually know how to sample a random orientation. I think it takes a long time. That's part of why counting is NP complete, NP hard. But I did my best. I ran my Monte Carlo simulator for a long time, and this is a random sample, roughly, of this thing. And unfortunately, I don't have any theorems here. I just have a picture or two. But I think it calls out for some interesting interpretation here. Okay, finally, we can ask sort of the statistical mechanical question: can we use this to somehow count orientations, acyclic orientations, or in particular these bipolar orientations, which are again acyclic orientations with only one source and one sink? And well, here's a suggestion. I can't answer that question at the moment, but I have a start. So let's just put ourselves on a cylinder here. We'll attach all, one vertex on the left, attached to everybody on the left, one with value 0 and one with value 1 over on the right. And now that n-harmonic equation gives us, suppose we were looking for a function on the vertices which would have energy 1. An energy 1 harmonic function, n-harmonic function. Then at every vertex, it satisfies an equation linking the value there and the value of the 4 neighbors. At every vertex like this one, there's a relation between it and its 4 neighbors. And if you solve for the neighbor on the right, xi plus 1j, in terms of the other 4 neighbors, the neighbors to its left, you get a recurrence relation giving the value on the right in terms of the values on the left. It's like a transfer matrix sort of equation. It's just a nice rational equation. Here it is, explicitly. So, starting from some values on the first row, you can use the recursion to, go all the way across with this composition of rational functions, and at the end, you have to get all values 1. And so I went through a fairly lengthy calculation hidden between here to compute the growth of the degree of xij as a function of the. So I just put variables on the first row, and you compute the degree growth of xij as a function of I, as I goes across, and it grows roughly it grows asymptotically when the cylinder gets large at rate 4 to the I. So which would indicate that there are at most 4 to the number of vertices solutions to this equation. But that's sort of a trivial upper bound, because if you're counting orientations, at each vertex there are twice as many edges as vertices, and each edge has 2 orientations, so that gives you 4 per vertex. So this is just an upper bound, but gone through an extremely painful process. But so now there's a more refined argument which will, in principle, tell me exactly how many solutions there are when I get to the end. I just haven't carried it out yet. So that's my next step. So I'll stop here. Thank you.
Questions?
Yes.
Can you directly use your methods if your graph is infinite? Say, for example, the programs that Google had used with what is the...
Nothing, I don't need planarity anywhere.
No, I did not speak about planarity case, but I was speaking about finiteness. Do you have some infinite graphs that you can create? And here it is essentially Z2, but all of Z2, and you look for the only harmonic function that is 0 at infinity or negative everywhere.
There is no such function. In principle, you can do this for, not for Z2, there's no.
It's something with one over T that is decreasing as a gun.
Yes, in principle, you can do this for infinite graphs, so by taking limits of finite exhaustion, sub-exhaustion, initial conversion. I think that's the short answer, but maybe that's not the question you really asked.
So maybe a related question,
Yeah.
which is maybe closer to what you're doing. What if you do it on torus? So without a sink
Yes.
and a...
Yes, so there's an analog on a torus where you fix the homology class. So the analog of harmonic, there is a harmonic function on a torus where you fix the homology class of your harmonic function, harmonic one form, and then you can find that harmonic one form in that homology class, and then look at its orientation, and you can find one which has your desired energies, like all energies one.
So the theorem still holds.
theorem still holds in that case, yes.
Other questions?
Yes.
What is the relationship with dessin d'enfant?
Oh, yeah, the reason, Grothendieck defined these descent d'enfant was that there was this Galois group action on these figures which he wanted to understand. And here we have a very similar situation, except that the underlying number field is totally real, but except for that, and then the action of the Galois group is on the set of acyclic orientations of a graph. So that's the sort of the totally real, I think of that as a totally real analog of the descent d'enfant. You have a graph with some boundary values, and then the Galois group permutes the orientations.
But the coordinate theory was really related to the Riemann sphere, whereas you don't have anything like the Riemann sphere anywhere.
That's right. Right, there's less geometry in what I'm doing, but
That's
nonetheless, these objects are still, well, the geometry is hidden in that, there is geometry. I mean, you saw those pictures. If the graph happened to be planar, I could draw a picture which is an actual sort of geometrization of the graph. So in that sense, it is analogous. Yes?
Can you specify a bit more when you pose this question about how does a random orientation look like? Or, what should be random? Should be the distribution of areas should be random, or of course subject to this constraint?
Well, all I want is a uniform random acyclic orientation of the graph. And then when I draw that picture, is there some sort of measure? Does the picture converge in some sense if I start with a uniform random orientation? There's a natural measure on these finite pictures, but in the scaling limit, maybe that it actually, there's no randomness and it converges to some sort of nice limit shape, where the randomness is sort of washed out. There's maybe some concentration of measure phenomenon in the limit. I don't know if there is.
No, yes. It's actually related to your previous remarks. So maybe, is there any hypothetical relation to plane partitions or whatever of this sort, where we do have algebraic curves?
Not that I know of, no. Yes. Can't say anything about that.
There are no more questions? That's thank you for tuning in.